Warshall's algorithm. Let's take a problem. We would like to know if one vertex is reachable from another, but we are not worried about how many intermediate vertices we need to go through. For example, can I leave from the Chattanooga airport and get to Papua New Guinea? Obviously not directly, but I can do it if I change flights enough. Solutions. Given a graph representation of the airline routes, I could run a DFS or a BFS. And if I use a BFS, I'll even get the route to do it with the fewest number of edges or flights. But these are not fast algorithms, as we'll see when we start looking at the big O. So if I have to run a DFS or a BFS every time I have one of these questions, I'm going to choose some computer time. So the Wahrshall approach is to calculate all these connections once and pay a bit of a price, as we'll see, and then save the calculation in such a way that we have a fast lookup. Here's an example. Here's a small connected graph on the left, 5 vertices. And on the right, I've got the adjacency matrix representation. So you can see from A, I get to C, from B, I get to A. You know, it's very straightforward. C, I don't get anywhere. D, I get to E. E, I get to C. So we take this matrix for our example and we'll apply Warshall's. And to apply Warshall's, we start with the first row. In this case, we'll call it row A. And we start scanning across column by column. And eventually we find a column that has a 1 in it. In this case, row A. We find a column of row A that has a 1 in it. In this case, that would be column C. That's the first place we find something. This means that from A, you can get to C, which I'll notate as A arrow C. If A goes to C, what goes to A? Well, I can express this as question mark for what, arrow A, arrow, and that should be a C there. To find out what goes to A, we look down the A column. And when we find a 1 in the A column, we know that that's something that can get to A. Or that A, yes, that can get to A. So step 2, we find a 1 in row B. So we now know that B can go to A and that A goes to C. So if B goes to A and A goes to C, then B goes to C. Not directly, it goes there through A, but from B I can in fact get to C. So I'm going to fill, so that means that B goes to C, and I'm going to fill a 1 in to show that B can go to C. And so I start filling in my adjacency matrix. So I keep going. I go through each row, and each time I find a 1, I go to a related column. And each time you find a 1 in that column, we fill a new 1 into the array. So for our example, we've already done where we found B, but we find later on that we can fill in that D goes to C indirectly, and we fill that in. And at this point, we now have something where we can directly look up all the places we can get to from a given starting point. How do we implement this? Well, I actually posted some code on the in Canvas for you to look at if you care. But the common approach is a triple loop where we loop through the rows, right? So that's one loop. And then within that, we loop through the columns. So that's a conventional nested loop. And then I have an if statement, and if a 1 is found, then I'm going to loop through the column for that row. And if I find a 1 in that column, then I'm going to make a new assignment into the table to indicate the new relationship that I found, the indirect relationship. This means that Warshall's has a big O of n cubed, n to the third, to calculate the table. But once I have the new matrix filled in, I can simply look things up. And that's a big O of 1, because looking up in a two-dimensional array is a simple calculation no matter how big the array is. So that's Warshall's, and that's the end of chapter 13. We'll do a couple of algorithms, and then we'll move on to chapter 14 next.